All right, in the last video, we started chapter 14 and we were talking about the average rate of a reaction. And we kind of learned that that's pretty limited because depending on whether you pick the beginning of the reaction or the really long time, your slope's going to change. So what we use instead typically is something called a rate law. And what this does is this relates reaction rate to the concentration of reactants. So we said at the end of the last video that the higher the concentration, the faster the reaction is going to go. Well, we want to be able to predict what the reaction rate's going to be if you know those concentrations, and that's what this is for. Okay, rate laws always follow this general form. I will not give you this equation. I need you to learn this because this is just kind of the standard way that they're all set up, and it does depend on the reaction. But they always follow the same generic formula. The rate at any given moment is equal to K, which is a constant we'll have to figure out, and I'll show you how to do that, times the concentration of one of the reactants. If you have like two reactants, it would look like this, raised to some exponent. Some textbooks use like X and Y. The textbook I stole this from uses M and N, okay, times the concentration of whatever the next thing is raised to the N. Okay, so I need to label a few of these things. So this rate, we just talked about in the last video that it kind of depends on what you measure. We try to measure the smallest increment possible at the beginning of the reaction. So basically the initial rate. Partly because that's the only time that these initial concentrations are going to matter. Okay. K is literally just a constant. It varies from reaction to reaction. It's also temperature dependent. We'll have to deal with that later. Okay. Yeah, I'm gonna switch colors here just for variety. A and B are the initial concentrations of the reactants. And M and N are, there's always a exponential relationship. Basically, you know, if this is a 2, what this means is every time you double the concentration, the rate's going to be 2 squared. It's going to go up by a factor of 4. These are exponents for this. Oops, exponents, and they're always small whole numbers. So they're always like 0, 1, 2, 3, or 4. You're never going to get decimals. You're always going to have like nice, even numbers. Okay. Here's where the fun bit kicks in. Fun being the most sarcastic word I can find right now. You cannot just look at a reaction and know how this is going to look. You have to solve for like K and M and N to get all these numbers. You actually have to use experimental data. Okay. Unfortunately, this is one of those topics that I actually think is not all that difficult, but students kind of struggle with this. So we will definitely do examples in class on top of the examples I'm going to put in here. But there's really no cheat way to do this. You kind of have to jump in the deep end and actually just do one of these problems. And I'll talk through, try to explain what I'm doing, but we're going to have to do that. Okay, I'm going to start a whole new sheet of paper here. So let's just look at a random example. So this is one I stole out of a textbook. So let's say we have this reaction. 2 moles of NO plus Cl2 forms 2 moles of NoCl. Okay, doesn't even matter what this reaction is, has no bearing on this whatsoever. What we know is that even without any of the data that we're going to need, the general form of the rate law is going to be rate equals K times each of these things raised to some unknown exponent. It would be nice if it was just the coefficients, but we can't. It might be, but it's more of a coincidence if it is. But some unknown exponent times this thing raised to some other unknown exponent. So our main goals right now are based off a table of data that I'm going to have to put up here. We need to solve for k and m and n. Everything else we leave as is, okay? So the idea is if we were given initial concentrations and we had the exponents and the k value, we could tell what the rate was going to be. That's kind of the point of all this. So to do these problems, you will have to be given a table of data. So this is just a table of data that I stole from a textbook. We're going to try an example. So what we would need is the two reactants. We would need their initial concentrations. They're going to be in terms of molarity. That's supposed to be a bracket. I can't draw. Okay. And then we would know the initial rate of the reaction in terms of molar per second. And unfortunately, you have to have at least 3 trials for this to make any sense. Okay. So, I'm just going to start writing down the data that was in the textbook. We'll see what happens. Okay, we know so little about this, we don't even know if this is a fast reaction rate or a slow reaction rate. We have no idea, okay? And then what we do is we vary the concentrations and see how it affects the rate. All right. Okay, so what we're really looking for out of this is you should solve for m and n first. It sounds almost counterintuitive to solve for the exponents first, but it's actually the easiest thing to solve for. So what we're looking for is if one of these two things doubles, we want to know, does the rate double? Does it does it quadruple? Does it go up by a factor of 8? Does it not change at all? Because these have to be nice whole numbers, if the rate doubles, if the concentration doubles, the rate is going to go up by a nice even factor. So like 2 to the 1, or 2 to the 2, or 2 to the 4, or 2 to the 3, or whatever, okay? So what we're looking for in this data, if we want to figure out what is the exponent for NO, which is m, if we're solving for m here, what we're looking for is NO to double, which it could be these two, or it could be these two. It's hard to know. But we also want this one to not be changing, because if they're both changing, it's hard to tell which one's affecting the rate. So what we want is this to be constant, which would be the top and the bottom one, and this one to be doubling, which would also be the top and the bottom. And what we see is that 0.0125 going up to 0.0250 is doubling. Hopefully it's obvious, but just in case, I'll plug it in just to prove it. Hey, it came out to a factor of 2. So what we see is that it doubled. It went up by a factor of 2. And we want to see what happens to the rate when you do that. Okay, so if this went up by a factor of 2, we want to see how this goes up. So what we're going to do is we're going to take the bigger number divided by the smaller number. So 9.08 e to the negative 5th, which is the same thing as times 10 to the negative 5th, divided by 2.27 e to the negative 5th. And I got 4. Okay, so when we doubled the concentration, the rate went up by a factor of 4. So the way this works is because the concentration was doubled and it's affected by that exponent, we can solve for the exponent like this. So for this one, it would be this went up by a factor of 2, and the exponent is m, that's what we're solving for, and the rate went up by a factor of 4. Now, we could go through some really horrifying math and logarithms and just horrible stuff and take like the log base 2 of both sides, which if you have a really expensive calculator, you might be able to do. Or we can just realize that this m number has to be a nice whole number. So 2 to the 1 is 2. 2 squared is 4. So m has to be 2. Okay, so let me try to walk through that again. In terms of deciding everything, what we want, since we're solving for m, we want the exponent that it applies to, we want that thing to double while the other one stays constant. So we did 0.0125 to 0.0252 because that's where, or 250 because that's where it doubled. And this one wasn't changing. So like for trial 1 and 3, this was unchanged while this doubled. And then we see how it affects the rate. So this doubled and this went up by a factor of 4. So because this doubled and it has an exponent to it, we can do 2, because it doubled, 2 to the m, and see how the rate changes, which comes out to a 4. 2 to the 2 equals 4, so m has to be 2. Okay, I'm going to try to switch colors here and try for the other one. So if we're solving for n, now what we're looking for is Cl2 to double while the NO is constant. So for NO, it's constant in the first two, right? It's not changing. The third one's where it changes. These two are the same, and this one, it doubles. So I'm going to do this one in red, and it doubled again. These are always going to be set up so that they double. It's just kind of how this is done. And now we're going to look over here to see how the rate changes. So we're going to take 4.55 e to the negative fifth divided by 2.27 e to the negative fifth. And, you know, it's got a few little decimals, but it's basically 2. So, to solve for n, because Cl2 is the one that we're looking at changing, I'm going to run out of space here. Well, let's do this over here. We saw that when the concentration doubled, this is the one that has an exponent of n, the rate also doubled. So the only mathematical way for this to make any sense is if n is equal to 1. Okay, so we literally just solved for both of our exponents. M is 2, n is 1. It is pure coincidence that that's the coefficients in the front. You cannot just blindly put the coefficients as your exponents. It just happened to work out for this one. Okay, well, our job is to solve for k, m, and n. We've already got m and n, so now let's solve for k. What we're going to do for that is we're going to pick one line of data. It doesn't matter which line. It should give you the same answer no matter what. I almost always pick the top line. So we're literally going to use this generic equation that we haven't solved everything for, and we're going to set it up. So I'm rewriting it just so that it's clear. Okay. And now what we're going to do is we're going to plug in everything that we can. We know m and n because we just solved for them, and we know these concentrations, and we know the rate. So we should be able to solve for everything except for k. So for the first one, this is 2.27 times 10 to the negative fifth molar per second. The units get a little weird on k. It kind of depends on what the exponents are. The only way you're going to be able to figure it out is by plugging in the units as you go. K is what we're solving for. For the first reaction, the concentration of NO is 0.0125 molar, and the exponent is a 2, because we just solved for that, times concentration of Cl2, which is 0.0255 molar, and that exponent is a 1, which we don't really have to write, but I'm just going to for clarity's sake. Well, we have everything plugged in except for k. We just rearrange and solve for k. So, for algebra's sake, I guess I'll show my work. Do my work in blue here. What we would do is divide out what we can. So on this side, that's going to cancel out, and that's going to cancel out. So k is equal to all of this jargon. Okay, so if you plug everything in, we would take 2.27 e to the negative fifth divided by 0.0125 squared. You took the time to solve for the exponent, don't forget to plug it in. And I'm going to hit equals because otherwise I have to be really careful with parentheses. This is also on the bottom, so I'm also going to hit divided by 0.0255. Okay. And I got 5.70, I guess. In terms of units, this gets a little weird now. I'm going to use red, I guess, to cancel stuff out. So we have molar here, and molar squared here, and molar here, and inverse seconds. So the molars are going to cancel out, And what we have is seconds on the bottom of this, and then this is also being divided, so it's also on the bottom. So we have seconds on the bottom and molar squared on the bottom. The units are going to be weird for K, and they do matter. Typically, chemists write it like this. Okay. This, if you're curious, if you're confused by this, this means 1 over molar squared seconds. Okay. Now, what we have done is we took the time to solve for m, we took the time to solve for n, and we solved for k. Now we need to plug those three things back in to get a rate law that makes any sense. So, we solved for k, so we're going to plug that in. Inverse molar squared, inverse seconds, times concentration of NO squared times concentration of Cl2. This is our rate law for this reaction with this set of data. Okay, so for these problems, I would have to give you data to work with. Okay, so real fast, let's try an example just to see how to apply this to something. Now that we've got this rate law, what the hell do we do with it? Okay, so we want to know, if we ran this reaction, we want to know what is the rate if the concentration of NO is equal to 0.231 molar and the concentration of Cl2 is equal to 0.0941 molar. Okay, you'll note from our last set of data that 0.231 is significantly higher than any of our numbers, like a factor of 10 higher, and 0.09 is also at least almost double the highest value we have. So these are well outside of the range of what we have measured, but the rate law should work for any concentration. So we're going to take this equation that we just solved for, and that's going to be where we start. Just rewriting it so it's on the same page here. So we just went through all this legwork to solve for k and m and n. We got the constant and the exponents. But now we can apply this to situations that are outside of the range of values that we have started with. So we're just going to plug everything in. We're solving for rate. We don't even have to rearrange anything. So it's 5.70 inverse molar squared, inverse seconds. NO is 0.231 molar squared times concentration of Cl, which is 0.0941 molar. In terms of units here, this molar is squared, and this is 1 over molar squared, so those would cancel out. And we end up with molar divided by seconds, which is great because that's the units we use for rate, molar per second. If you plug all this in, and you're really, really careful, because I'll type everything in so you can see it, 5.70 times 0.231 squared times 0.0941. Okay, we get a value of 0.0286 molar per second. This is how fast the reaction would go at these concentrations. And if we look at this, you'll notice that our rates were really, really small numbers before because we had really low concentrations, and we said that the rate should go up at higher concentrations. Since these are higher concentrations, the rate is significantly faster, and that makes sense, okay? We will do a lot of examples of these. They're kind of a pain. I actually don't really dislike these problems, but students tend to freak out, so we'll do a lot of examples. All right, thank you.